Yay. Okay. So, 3-1, it's actually the warm-up exponential functions. All right. I'm going to drag you through some horrible stuff. Ready? Horrible number 1. Things that you should know already, but I don't trust it. So I'm going to throw it all out at you at once. First thing, when you're dealing with an exponential function, the general form is written this way. Function notation, of course, equals b raised to the x power. Now these are different than normal functions because up to this point you've basically dealt with the polynomial type functions where the x's are in the base and the powers are like square and cubed or square root, things like that. So sometimes people get really, really confused with exponential functions because it just looks a little strange, and they try to treat the x as a number, and you can't because it's an exponent. So laws of exponents kick in. And I'll review those really quickly in a second. But I wanted to talk about the function as a whole first. First off, can b be any number? In other words, is the value of b, could it be any real number possible?
Yeah.
You think so?
Yeah.
And still be a function? Let's try it. So if b is equal to 1, we would get f of x is equal to 1 to the x. What's 1 to the x equal to? 1. It's called a trivial function because it's not an exponential function anymore, it's a constant function of 1. So usually when you're talking about...
Hey, Mr. Cologne, sorry to bother you. I think borrow about 2 tables and about 4 chairs and I'll bring them back.
This goes on my recording. Thanks. Just go ahead.
You ready to spread it?
I'll delete this part. Why are you stealing this stuff from me?
You ready to run? Ready to run.
He likes making things difficult.
Another place to say, bro.
Why you tell me you were recording?
You knocked on my door. What am I supposed to say?
Get out.
Come on, muscles.
Gotcha.
You gonna take a chair, Stu? Typical day at Edgecombe Community College.
Get out.
Might as well start over.
Nah. I'll just delete. I can delete a chunk of the video from beginning to wherever. I'll just do this. And it shows up. Ooh, alright. So b being 1 is kind of irrelevant because it brings you back to a constant function, and a constant function definitely is not what I consider a exponential function. So guess what? B can't be 1. Alright, what about 0? If you make b equal to 0, you're going to get f of x is equal to 0 to the x, which is 0. Well, that's trivial too. So we're going to throw away 0. So far, b can't be 1 and it can't be 0. So far, so good. Can it be a fraction?
Yeah.
Yeah, I mean, 1/2 raised to the second, 1/2 raised to the third, 1/2 raised to the negative third. It really doesn't matter. You're going to get some kind of answer out of it, and it's going to be different every time you choose a different x value. So it's not a constant function. So numbers that are between 0 and 1, perfectly fine. What about bigger than 1?
Or
Those work too. 2, 3, 4, 5, whatever you want, raised to some power. You're always going to get different answers, and you'll still have like 5 to the x. It'll look like an exponential function. So the next question then becomes, and I'll just use -1 as an example. Oh, -1's decent. Let's make it -2. That makes it even more apparent. Now, if I let b equal -2, is that an exponential function? All right, let's look at it. F of x is equal to -2 raised to the x power. you think that's a function? Or does it make a nice function?
It's a function.
You think? It is a function, but there's something else that I really, really want, and I'll give you an example. We do a table of values. Here's x, here's y, and I choose -2. When x is equal to 2, -2, it's -2 raised to the -2. What's that equal to?
4.
Close, no cigar.
-4.
What's negative exponents mean? When you have 2 raised to the -1.
It's 1/2.
1/4. So it's a positive 1/4. All right, if it's -1, what's -2 raised to the -1?
-1.
Negative.
Wait, are we talking about the exponent here right now?
Yeah, when you have a negative exponent, like a to the -1, that's the same thing as 1 over a. It's always a reciprocal. It's actually literally called the reciprocal function.
Yeah.
So if -2 is raised to the -1, it's reciprocal. So what's the reciprocal of -2?
1/2.
-1/2.
Yeah.
Because the power is odd, the negative stays. So you get -1/2. 0. Anything raised to the 0 is equal to?
0.
Oh, I swear.
Oh, it's not real.
No. Back over here. If I have a to the 3rd divided by a to the 3rd, what's the law of exponents say about
That's 1.
base over base? What do you do with the exponents?
Cancel.
Stop that. They
Multiply.
subtract. You subtract the exponents,
Oh,
right?
yeah, you do subtract.
So this would be a to the 0. But a to the 3rd over a to the 3rd is equal to 1, because anything divided by itself is equal to 1 except for 0. So this is 1. Anything raised to the 0 is equal to 1.
You should put a lot of those on the test we took.
Oh my lord, anything raised to the 0. If I put in 1, what's -2 raised to the first power? Well, -2, right?
Mm.
If I put in 2, -2 raised to the second power is?
4.
4. The problem with this function is it bounces back and forth between positive and
Negative.
negative. Second problem,
This is algebra or
it's just regular algebra. Exponents. Laws of exponents is actually college algebra. If I put a half here, what's a half power represent?
Half power.
Yeah, what's a half a power represent normally?
0.5. It's
X raised to the 1/2 power, what's it represent?
x to the 1/2 power.
I swear. If I have 4 raised to the 1/2 power, what's it equal to?
2.
2. Why? Because the half power represents?
So it's 1 over x.
Stop it. What's a half power represent? Why is that equal to? It's not 4 times a half.
Because you take the square root of it.
Square root, thank you. So when you do a half power, it's a square root. What's the square root of -2?
There isn't.
There isn't one. So this is undefined. It's an imaginary number. You can't plot it on a piece of graph paper. So not only does the function go positive, negative, depending on if you're even or odd, but if you start getting into fractions with even denominators, you're always going to have an undefined point. So this graph, if we were going to graph it, would look like, and then there would be these big holes that nothing was in. Do you think that should be a nice function?
No, that would be nice.
I mean, usually we like functions to be, curves, smooth, continuous, infinite possibilities. So what we do with this is we say that b can be on the interval from 0 to 1 and 1 to infinity. The base can be anything in there, but it cannot be negative, it cannot be 0, and it cannot be 1. Does that make sense? So when we talk about b, we can't let it be those numbers. Bases are never going to be negative, they're never going to be 1, they're never going to be 0. Now, x, on the other hand, can be anything you want it to be. So the domain is negative infinity to positive infinity. You can raise a base to any power you can imagine. Seriously, you can have 2 raised to the square root of 3 power. That's totally legal. Hard to prove that it does exist, that takes calculus, but you can do it. Calculator will spit out an answer all the time.
The domain of an exponential
Function is all the way to the left, all the way to the right. Now the range is a little different, we'll talk about that in a little bit. So I guess what I should do next, since I had to come over here and talk about laws of exponents yet again, let's do laws of exponents. Just some of them, not all of them. So the ones you need to know, a to the m times a to the n is equal to, now notice the bases are exactly the same. What do you do with the exponents?
A M times plus
Which one?
the M and N.
Add them or multiply them?
Add them.
You sure?
I think so.
You want to prove?
Yeah, you can prove it.
No, real easy. Ready? Fingered proof. A squared times a cubed. How many a's will you have?
A 6 or 5.
How many a's will you have? I mean, that's really what's happening. You have 2 factors of a over here and 3 factors of a over here. So if I multiply them, how many factors of a do I have? 5. So you add the exponents. So this would be a to the m plus n. Okay. Law number 2 of the important laws. A to the m over a to the n. When you have factors common top to bottom, you're going to be canceling them out and replacing them with 1, because a divided by a is 1. So what happens to the exponents? You subtract them. We talked about that over there. So this is a to the m minus n. Law number 3 of the most important laws of exponents. A to the m raised to the n. Now the language on this is really strange. Like a to the m is m factors of a, so you would have m of them. And a to the n is n factors of a, so you would have n of them. Well, this one reads n factors of m factors of a. So take a guess what you do with the m and the n. Multiply them, because you're going to have this many of this many. It's like saying, I have 5 dozen eggs. So how many eggs do I have? Well, 5 times 12. So this becomes a to the mn. The one you memorize is this one. A power to a power you multiply. Therefore, when you get base times base, you know not to multiply, because this is the multiply one. That was the add one. What's the other one? This one actually comes from the division. A to the negative n is the same thing as 1 over a to the positive n. It comes from the division one, because when you subtract and you have a small number on the top and the big number on the bottom, you're going to get a negative exponent. So the way to fix that is to force the factor into the bottom and change the sign on the exponent. Of course, you can go backwards with this. If it's negative in the bottom, you can yank it and put it in the top as a positive exponent. And then, of course, a to the 0 is equal to 1, which is also a subtraction property. Now, there are a couple others, but I don't think we have to get into it specifically. Probably one more that you might want to be aware of. If you have 2x cubed raised to the 5th power, what's it equal to?
2. Oh wait, no, it's what is it?
Well, don't tell me the answer is 2 to the 5th, x to the
15.
15th. The power on the outside kind of distributes, but don't think of it as distribution, because if I write this, is that the same thing as x to the 15th plus 8?
No.
Heck no. Not even close. This thing is equal to x cubed plus 2 times x cubed plus 2, and you'd have 5 of them. 5 factors. So be careful. Laws of exponents only work on multiplication and division. They do not work on addition and subtraction. And that's why this does not equal this. For those that love doing things like that. Because this thing is a half power, and laws of exponents do not work on addition and subtraction, so you just stop. So when you see addition and subtraction, don't be thinking anything, just leave it alone for a little bit until you can simplify it normally. Okay, so those are laws of exponents. And a little bit about exponential functions. So let's go a little deeper. Add a page. Erase all this mess. The best way to look at a function, I think, is graphically. You can see its behavior, figure out its domain and range and all that fun stuff. So let's look at a basic function. Let's write it. Basic function. For example, we want to graph the function f of x is equal to 2 to the x. I want to graph this function. Do you know what it looks like? If you don't, can you find out?
Yeah.
How would you find out?
Plugins.
Plug in a bunch of values and generate points, right? What's that called? When you start plugging in values, what do you create? Not the graph, but before the graph. Plug in values, generate y's. It's a table.
No, table.
Table, not a graph. The table first. So you set up a table. I'm actually going to set up 2 of them. First table, x, and then what we're going to do is plug it into 2 to the x. Now, what kind of values of x should you always choose? Positive?
Yeah.
0, 1, 2, 3, 4, 5?
No.
Should you choose some negatives? Why not?
That way you can't have anything, can't you?
I can have anything.
Yeah.
Because I've already defined negative exponents work perfectly fine. So when you graph something, you should always pick a few negatives, 0, and a few positives, just to get a good feel. Because most graphs behave nicely around the origin. Remember transformation of graphs? We always had that origin point to move around. This is similar, but it doesn't have an origin point per se, because if I plug in 0, I don't get 0, I get 1. So we got to be careful of that. So I'm going to start with negative 3. What's 2 raised to the negative 3 power?
Negative. It's 8.
No,
9.
no,
Negative 1 over 8.
negative 1 over 8?
8.
Negative 1 over 8?
You're saying 8. I was saying 8.
I'm saying 8, but you said negative.
That was positive?
Positive. Why would it be negative?
I just
All a negative exponent is wrong side of the fraction. So this would be 2 to the negative 3, which is the same thing as 1 over 2 to the third, which is the same thing as an eighth. Negative exponents are reciprocals.
It'll always be positive.
Well, if the, yeah, this will always be positive for now. What if I plug in negative 2?
And it'd be 1 over 4.
It'd be 1 over 4. If I plug in negative 1,
It'd be 2.
1 over 2. If I plug in 0,
That would be 1.
it'd be 1. I love that now. It used to be 0, remember? Now it's 1. If I plug in 1, you get 2. You plug in 2, you get 4. You plug in 3, you get 8. Those are the easy numbers. 2 to the first, 2 to the second, 2 to the third. Great. So let's graph this. I don't need to go down. There's no negative y values. So this graph is totally above the x-axis. Will it always be above the x-axis? That'll be my next question in a few. So here's 1, 2, 3, you have negative 3, and 3, positive 3. And we're going to need 1, 2, 3, 4, 5, 6, 7, 8 going up.
That one line's like a lot bigger than all of those.
What's that?
That one line's like way bigger than every single one.
Which one? This one?
That one up top.
Oh, this one? 1, 2, 3, 4, 5. I always make my 5s bigger so it's easier to get to 10 and 15.
Oh, that makes sense.
You never learned that? No. Oh, I always do that. I don't know why. Alright, so at negative 3, you're at an eighth. Now an eighth is really close to the x-axis, but it's still above it. Now when you draw a point, it's actually a lot larger than a point really should be, because a point is no width and no depth to it. There's nothing, no dimension. It's just a position at a very particular point. Alright, if I go to negative 2, it's a little higher, a quarter, maybe up here. If I go to negative 1, it's a little bit higher, about a half. And then the fun things start happening. If it's 0, you're at 1. If you're at 1, you're at 2. If you're at 2, you're at 4. If you're at 3, you're at 8. Way up there. If you're at 4, you're at,
I'm sorry.
if x is equal to 4,
Oh,
16. It's basically off my board. So you can see that this thing is going to take off. That's what's called exponential growth. Now what's interesting is not the exponential growth part of it, it's what's happening on the negative side. If If I go to -4, it becomes 1/16. If I go to -5, it becomes 1/32. If I go to -6, it becomes 1/64.
Yeah,
That number is going to keep getting down and down and down, but is it ever going to touch the x-axis? No, because half of a half of a half of a half forever is always going to leave you something, even though it's really, really tiny. So when I draw this part of the graph, what does the x-axis become? There's a name for it. I don't think you would know it. Did we talk about asymptotes before? We talked about those dotted lines and transformations, right? Well, one of the things those dotted lines can become is what's called an asymptote. This x-axis becomes known as a horizontal asymptote. In other words, as x goes to -infinity, the function itself is getting closer and closer to 0. Now these little arrows are not equal to, because you cannot be equal to infinity. Because once you get there, there's always one more. In this case, one less. So when I say f of x is getting close to 0, that means it's getting smaller and smaller and coming closer and closer to 0, but it never ever touches it. So this horizontal asymptote is defined this way. You take x off to a direction, and the value approaches a specific value, in this case, 0. That's called a horizontal asymptote. On the other side, this graph just takes off, grows exponentially, and it'll just go off to infinity. Okay? So just by looking at this graph, what is the domain of it? How far to the left?
Negative infinity.
How far to the right?
Negative, or positive.
Positive infinity. What's the range?
It is.
How far down does it go? It's greater than 0. So what you do is you put a parentheses 0. It can't be 0. So it's a little bit bigger than 0. What's the max of the range? Infinity. And there's your domain and range of an exponential function. So you can plug anything you want into a exponential function, but the answers it spits out are always going to be positive. No matter what, your answer is always going to be positive. That's what the range tells you. Remember transformations?
Yeah.
We could transform this graph.
Just be the opposite way.
If you're going to do a base graph, remember base graphs are basically what it looks like. It doesn't have all the points. It only plots one point and the general shape of the curve, right? Just like if we were moving x squared around and we wrote x squared plus 1, we would just draw the 0, 1, and then the parabola from it. So the base graph of an exponential function, specifically this one, I consider this a base graph, it would look something like this. You would draw it this way. You would plot this point. This would be your origin point. Even though it doesn't start at the origin, you plot that point because it's one of the nicer points on the graph, 0, 1. So you plot 0, 1, and on the left-hand side, this graph goes down and approaches that horizontal asymptote. So another portion of your graph is going to be a horizontal asymptote. And then the other part just grows without bound. Grows without bound. So what if I want to draw this graph? What would you do?
You go up 3.
You would move up 3. And in this case, if you didn't use those dotted lines before when we were transforming, you have to now, because I need a reference line for my asymptote. So I need to take the x-axis and move it up 3 units to this line here, y equals 3. Where would my origin point go, my 0, 1 go?
0, 3.
It would go at this point 3, and it would move up 1. Because remember, the origin point is 1 high from your cross. So 1 high from my cross is happening here. That's where my cross is, right? Where the horizontal asymptote is hitting my other line. So you have to go 1 high. Well, what's the coordinate of 1 high?
0, 4.
0, 4. So this graph is going through 0, 4. It's going to have the same shape, right? So it's going to go and follow this as a horizontal asymptote to the left and grow exponentially on the right. And that would be the transformation of 2 to the x up 3. Does that make sense? So exponential functions always go to the cross and you either go up 1, or if it's flipped, you go down 1. All right, how about g of x is equal to negative 2 to the x minus 3. What would you do here?
You go down
You would go down 3.
and up one.
You would go down 3.
You would up one.
Let's go down 3 first.
Alright.
Just because that's a good start. So this is down 3, right? So you go down 3. So this would be y equals negative 3. What does this negative do sitting in front of the function? Flips it. So it takes your original graph, which was on the positive side, and flips it down to the negative side. So where's your origin point going to be? Negative 4. The graph got flipped. So it's going to flip over this line y equals 3. So what was going up 1 would go down 1. Does that make sense?
Yeah, I got it.
Okay. So the general shape is going to be the same. It's going to approach the horizontal asymptote on the left and grow exponentially on the right. Except here, to approach the horizontal asymptote, you actually have to go up. And to grow exponentially, you have to actually go exponentially down. So this would be the graph flipped and down 3. Not hard, right? I don't have enough room. Let me move this. There is one more possibility, and I'm going to show you 2 different ways of doing it. Well, at least try to. There we go. How about g of x is equal to 2 times 2 to the x. Now, if you go back to the transformation of functions, the 2 sitting in front of the function makes it get closer to the vertical, right? But that doesn't apply when we're talking about exponential functions. They do something a little different. And here's what they do. The bases here are exactly the same. They're both 2's. So what do I do with their exponents?
The same. Or add.
Add them. So what is this really equal to?
1 plus x.
Well, you can write it out. I usually write x plus 1, but that's just me. I put variables first. So it's 2 raised to the x plus 1. So originally we would think that it gets closer to the vertical, but we can't draw it that way because that's not really what's going on transformation-wise. Because after we change it, what does the plus 1 actually do to the graph?
It moves it up
Moving up and down is outside the function. This is inside the function. It's near the x. What happens when numbers are near an x? They affect the x value somehow. So what does the plus 1 do to the x's?
one. Move it to the right.
Moves it to the left. Remember, if it's inside, opposite direction. You know, if you're graphing x minus 3 squared, which way does it move?
To the right.
To the right 3 units. To get it equal to 0, x would have to equal positive 3. So it moves it 3 to the right. So to get this equal to 0, x would be negative 1. So it has to move it to the left 1. So this is going left 1. That's all we know about it. So you draw your graph. What kind of dotted line am I going to put in? Am I moving the y-axis, or the y value, or am I moving the x value? X value. So I'm going to be moving the y-axis. So I get it, this line here, which is x equals negative 1, 1 to the left. The cross is happening here. So which way do I move from the cross?
Move it to the left. Move it to the
From the cross here, you would go up 1. From the cross here, you know, the cross was here, you went down 1. So what do I do from the cross there?
Go to the left.
This was up 1, positive. This was down 1, negative. Which one's that?
Oh, you go up.
You go up 1. Naturally, you go up 1. If it was negative 2 to the x plus 1, it would be down 1. But it never goes left or right. The graph can move left or right, but that point is always going to go up 1 or down 1. So you move it up 1, what coordinate would this be?
Negative 1, 0.
Negative 1,
Or 1,
1. So you're moving up 1 from the x-axis. The graph would go to the left and approach its horizontal asymptote, which is the x-axis. Because it always goes to the left and approaches this x-axis, unless I do something else, and I'll do that next. And on the other side, it grows exponentially. That's all. Let's put it all together. One ugly graph.
Thought that was an asymptote.
What's that?
Thought that blue line was an asymptote.
The blue line is the reference of moving to the left one. The asymptote is always going to be horizontal for exponential functions. Now there are vertical asymptotes, but they're not for exponential functions because this thing goes negative infinity to positive infinity. If you have a vertical asymptote, your domain is going to be cut. It's going to stop someplace. All right, how about something really horrible? H of x is equal to 3 minus 2 to the x minus 3. Now, let's make that minus 4. Get back up here. Where's back up? Back up. Minus 4. All right, what's happening to this graph?
Going up 3 places.
Up 3? What's this minus 4 doing?
Draws to the right.
Right 4? What's the negative doing?
It is flipping.
And it's flipping it over the horizontal, but I very rarely flip over the vertical, but we'll see what it does if we do. All right, so if I'm going to graph this, what reference lines do I need specifically?
0.
Like this one, we move to the left and I put in x equals negative 1 as a reference line. This one is going right, so what do I put in?
Obviously, you need x equals 4.
X equals 4, so I'm going to put that over here. Here's x equals 4. Best to label these, because if you don't, you lose. I'm not doing dashes for this. I'm just doing the reference lines. That's all I'm doing. And what about the up 3?
If I'm y equals 3.
You're going to put in y equals 3, so here. And your cross is happening here. That's your reference cross. That's where you move everything from. So where do I go from my reference cross? You only have 2 directions.
Down.
Up or down?
Down.
This is down. Why?
Because of negative.
Because it's flipped. So instead of going up 1, you're going to go down 1. So what's the coordinate of this point?
Give me a
4, 1.
Close, no cigar.
4,
4, 2. You're only going down 1 from 3. So if you go down 1 from 3, you're only at 2. So this would be 4, 2. All right, what would the graph look like?
2. Yeah, it look like.
As you go to the left, where does it go?
Goes closer to 0.
It goes closer to
Or 3, excuse me.
y equals 3, the reference line. So it gets closer to the horizontal asymptote. And as it goes on the other side, it goes, because it grows negatively exponentially. You would have that graph. Does that make sense? All right. Will I ask a ton of these on a test? All I need is 1. Just to see if you know how to graph something that I throw at you. Is it the easiest question on my test? Heck yeah! Because all you're doing is drawing a little picture. Of course, then I can mess you up. So what happens? So far I've been dealing with the base being 2 all the time. That gets kind of boring. So what if I have f of x is equal to 1/2 raised to the x? What does that look like?
Yeah, plug it in.
Yeah, plug in values. So little table. I think we can figure it out from -2, -1, 0, 1, 2. It has the same general shape as the exponential function, but there's a slight difference. So here's x, here's 1/2 raised to the x. Alright. So what's 1/2 raised to the -2?
Is 1/4.
So close. When you see a negative exponent, think reciprocal.
Oh, so it is 4.
It's 4. You reciprocate the 1/2, it becomes 2. 2 squared is 4. What's a half raised to the negative 1? 2. What's a half raised to 0?
1.
1. What's a half raised to 1?
1/2.
What's a half raised to 2?
1/4.
Half raised to 3, 1/8, and so forth and so on. So when we graph this one, 1, 2, 1, 2, 1, 2, 3, 4. I'll put my big 5 in there, just for fun. When we plot this, negative 2 is at 4. So here's negative 2, 4. Negative 1, 2. 0, 1. 1 1/2. 2 1/4. 3 1/8, and so forth and so on. Where's my horizontal asymptote this time?
What's the problem?
This one was to the left. This horizontal asymptote is going to be to the right. So it's constantly decreasing as we move to the right, and as we move to the left, it's constantly increasing exponentially. So here you have x is going to positive infinity, and the function is going to 0. So the horizontal asymptote is on the positive side. All right, so how would you describe the difference between 2 to the x and half to the x? 2 to the x is constantly increasing. As you move from left to right, it's always increasing. 1/2 to the x is always decreasing. So this is what's called exponential growth, because it's growing exponentially. And this one is called exponential decay. It's called exponential decay because it's always decreasing. Think radioactive. Radioactive material decays over time. Turns into, well, if you start off with uranium-238, it turns into lead. So any piece of lead that you've ever fished with is radioactive. Isn't that a fun fact?
So everything you shoot with is radioactive?
Just slightly. Very, very, very slightly. Because uranium-238 turns into lead, and unless they process it perfectly, it'll have a little bit of radioactivity in it. I'm not sure if they process it perfectly. And once it already has something within it, it always does. Even, it's half of a half of a half. It's always going to be slightly radioactive. Nothing to kill you, but it's kind of a cool fact. All right, so when you're looking at that, this is messy. 1/2 raised to the x. Isn't that ugly looking? I don't like that. Because first off, you have to draw parentheses and all that fun stuff. So let's simplify. Laws of exponents allow me to do this. Right?
Yeah.
And 1 to the x is equal to
1.
1. So it's 1/2 to the x. That's still kind of messy. What if I yank 2 to the x to the top? What does it become?
2/1.
No.
Or 2/1.
What happens to the exponent? When I take an exponent and move it from one side of a
It
fraction
becomes
to
negative.
another, it becomes
Negative.
negative. So it becomes raised to the negative x. So f equals 1/2 x, 1/2 raised to the x. You can also write this function as f of x is equal to 2 to the negative x, which actually is better. Why? When you multiply a negative on the x, that takes your graph and flips it over the y-axis. So if you look at this, this is just the graph of exponential function normally flipped over the y-axis. Where it used to have a horizontal asymptote to the left, now it has a horizontal asymptote to the right. Where it used to grow to the right, now it's growing to the left. It just flips it over the y-axis. So trust me, you will never see 1/2 raised to the x from me. You will always see 2 raised to the negative x, or some fashion or form. I love classes that are small. You miss one person, it's happy. So, 3-1 continued. Quick review. Graphs are important because you can get domain and range right out of them. So, if you're graphing 2 to the x, it goes through this point, 0, 1. It has the negative x-axis as a horizontal asymptote, and then it shoots up to infinity. Okay. If you have f of x is equal to something smaller than 1 raised to the x, or equivalently raised to the negative exponent. This is what we were talking about last, that 1/2 raised to the x is the same thing as 2 raised to the negative x. Because that law of exponents, if you flip it, you have to change the exponential sign. Reciprocal function. And the graph of this one flips over the y-axis. It still goes through the point 0, 1. That becomes the important point, or what I call the origin point. But instead of the negative x-axis that's hugging, it's the positive x-axis. So it flips over the y-axis. So the top one we call exponential growth. Bacteria in a bowl, human population, whatever you want to talk about. The other one is called either exponential decay or just decay. Because it's constantly going down. Radioactive isotopes decay over time. If you have a war, populations decay over time. People are dying all the time, much more frequently. Alright, so those were the things that we talked about last week. So there's one other thing I want to talk about. 8th grade math. Remember 8th grade? A long time ago. Little chairs.
Chemistry?
Huh?
Chemistry.
8th grade math would be money, dealing with money. What? Don't steal any tables and chairs today. I never throw things away. You should know that. And one of the formulas for money was this. Compound interest formula. Remember this? That's a long time. Most people don't even realize it exists anymore. It's horrible. But this is how banks work. You put money in a bank, you get a little bit of interest one month, then you get interest on top of interest the next month, and interest on top of interest on top of interest the next month. And this is the formula that takes care of it, where n is the number of interest computations per year. And then, of course, t is years. Because we have to talk about the same time frame when we deal with formulas like this. Alright, so P is called principal. That's how much money you put into a bank. R is, of course, your interest rate. And A is the total amount of money that you end up with after a period of time. So if you want, you can think of this as a function of time, if everything else is fixed. So for instance, if I put $1,000 into an account that earns 6% interest, what do you think n would normally equal for a savings account if you earn interest every single month? What do you think n would equal? If n is the number of times you calculate interest per year and you get interest every month, what do you think n would equal? How many times would you compute interest in a year? Every month. So it would be 12. And then 12 up here. And let's say we kept this money in the account for 10 years. For 10 years. Got a calculator yet?
I left it in the garage.
I swear. Math classes.
I got one on my phone though.
That's not going to work. I'll tell you what it's equal to. By the way, even if you use your phone or whatever, this should be your first calculation because most people screw up here. So that's 120. And then all you have to do with this type it all in. And I think even on calculator phones, they do parentheses nicely too.
Yeah.
So 1,000 parentheses 1 plus 0.06 divided by 12 raised to the 120. Now this is 6% interest because it's 0.06. So it's 1819. And some change. So this is the total amount of money in your bank account after 10 years of just sitting there. So where'd the $819.40 come from? That's just interest. You know, the money that the bank pays you to let them hold on to your money. It's always a nice thing. Trust me, they don't pay 6%. They
Yeah.
pay 1. It used to be 5 way back when. It was a good interest rate back then.
Before the war?
Long before the 1980s. Yeah, way back. So this is something that happens with money all the time. So my question is, what happens if we compound it more? Does that mean we'll make more money? Because we're compounding interest more often? So what you can do is, you can change it to a week. So this would be compounded per week. How many weeks in a year approximately do you know? 52. I wonder if that's why there's 52 cards in the deck of cards. You ever wonder about that? And then this would be 52, and then the 10 years would still be the same. So if we do this calculation, see if I can edit really quickly. 52, that would be 520. This would turn out to be 1821.49. So if the bank changed from monthly to weekly, you only make about, what, $3 more? A little bit less than 3? Actually, $2 more. Ooh, how exciting. $2.09. So that's not a great big jump. What if we do it daily? My kids have that Fat Cat account at the State Credit Union, and they do their computations daily. So I'm like, oh, that's awesome, right? That should be a ton more money. But daily, how many days a year? 365. So this would be 365 times 10 years. So you would think these numbers are getting bigger and bigger, that this number is going to get larger and larger. So this one's going to take a little more editing. 365 and raised to the 3,650. So this comes out to be 1822.03. So now we've gone up 54 cents. So the first jump, and it basically, if you went back to annually to monthly, the annually to monthly is a big jump. The monthly to weekly is not such a big jump. The weekly to daily, I mean, 12 to 52 is maybe 4 times as big, about. 12 to 365 is a huge jump, 20 or more. But it's only going up very, very little. So each time we do this, the jump is getting smaller and smaller. And what that says, and it's a little hard to prove, but what it says is there's this maximum value that this thing is going to reach. So it's going to grow exponentially, but eventually it's going to level off to some value, some specific number, which is kind of cool if you think about it, that it's not going to get any higher than a certain number. It's not going off to infinity. It's not going off to infinity. It's being held down. And the number it's approaching is this. 182212. 182212. So even if I change 365 to 10,000 times a year, the biggest number it's ever going to reach is this one. Kind of cool, huh? In a weird way. Wake up a little bit. Show some excitement. But it's kind of cool because usually you're used to, if you calculate with larger numbers, your number gets larger continuously, especially if it's growing to begin with. But this thing is going to grow forever, but it only reaches a maximum value, which is kind of weird. So what we call that maximum value, or the reason behind it, is this. This is called a limit. Calculus notation. It's kind of fun. We're going to let n go off to infinity. So n never stops growing. So this number that I divide by is going to constantly keep getting bigger and bigger and bigger. And what I'm going to grow is this thing. There is a way of manipulating this formula to look a lot like that. And when you do that, you come up with a neat little formula. But right now, I just want to talk about part of it, the reason why it's reaching just this maximum value. So it kind of looks like the compound interest, except instead of 1 over n here, you have this r over n, but there's a way of manipulating so it's 1 over a number. And then this nt just becomes n if you ignore the t. If you ignore the t. This thing, if you calculate it, for large enough n's, becomes known as this number.
I've seen that.
And it's on a calculator, 2.7128, blah, 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 blah. It goes on forever. It's like pi. This is called the natural number. And it's natural because it describes growth really well. Growth of bacteria, decay of radioactive materials. So it just gets this fancy name called the natural number. On scientific calculators, sometimes they have the e by itself, but usually it's as a function e raised to a power. And then you have to put 1 in there to see what it's equal. But it's approximately 2.1. Let's be a little bit more precise. Make sure I get this right. 2.71. 2.71. 2.8. Never got the 7. And it goes on forever. So it's like pi. It's an irrational number. But it's really, really nice. Very nice number. But this is the pure definition of it. There's no other way of coming about with this number. Well, it's actually easier than pi. Pi's a pain in the butt to come around, but to find the value of pi, e's a little bit easier. Now, if you manipulate this formula enough, in other words, if I take a equals p parentheses 1 plus r over n raised to the nt, and I let n go off to infinity, as large as I want it to be, then this formula manipulates into this. It becomes a equals p e to the rt. So if you want to know what your maximum value of an account is, no matter how many compoundings happen, this is the formula you use. If you have a specific compounding, you use this one. I wish there was a bank out there that would do infinite compounding. That's a much easier formula to work with than this mess. All right, so that's e. The graph of e is exactly the same as this one. 2 to the x, e to the x, they all have that same look. They hug the negative x-axis, they go through 0, 1, and they shoot off to infinity. E to the negative x looks like this one. It hugs the positive x-axis and